A telescope located in Thailand recently captured a phenomenon that was completely unanticipated. We are seeing three tails, all pointing in totally different directions, emerging from a single comet. Now, if you possess any knowledge about how comets usually behave, how they react to solar wind, or how their tails generate and dissipate, you might already be feeling a tightness in your chest. The reason is simple. What you are observing in this specific image violates the fundamental timeline that every single astronomer anticipated. That anti-tail, the sharp beam of light aiming directly toward the sun, should have vanished by this time. It should have faded, dispersed into the vacuum of space, just like smoke in the wind. However, instead of fading, it is sharper than it was 1 month ago, and it is actually getting stronger. We are currently 32 days away from the closest approach. We are 32 days from the moment when Comet 3I Atlas makes its nearest path to Earth, a moment when every major telescope that can secure observing time will be focused on this object. But here is exactly what makes this image from Thailand so profoundly unsettling. We are not looking at the build-up phase anymore. We are looking at what is supposed to be the wind down, the calming period, the predictable fade that occurs after every comet rounds the sun and begins its journey back into deep space. Except 3I Atlas did not get that memo. And the more we investigate, the more we realize this is not just unusual. This represents a fundamental challenge to our existing models. Let me be crystal clear about what we are witnessing. This is not some blurry photograph taken from an amateur's backyard setup. This is a precise observation from a 26-meter telescope operated by Tiasak Talawang in Rayong, Thailand. The image processing is incredibly clean. The resolution is exceptional, and what it reveals is a triple tail configuration that exists simultaneously in a way that textbooks claim should not persist this long after perihelion. There is the ion tail, that thin bluish streamer pushed straight back by solar wind. There is the dust tail, broader and curved, following the gentle arc of expelled particles. And then, there is that anti-tail, that impossible spike of material pointing back toward the sun, almost as if the comet is somehow defying the very forces that shape it. Here is precisely why this matters more than any space headline you will read this entire month. Comets are predictable. They follow patterns established over centuries of observation. We understand the physics. Solar radiation pressure pushes dust away. Solar wind strips ions and carries them downstream. When Earth crosses a comet's orbital plane, we sometimes see an anti-tail, a geometrical illusion where large dust particles lagging behind the nucleus appear to point sunward from our perspective. But those anti-tails are temporary. They peak when we cross the plane, then fade over days or weeks as those heavy particles slow down and spread out. By the time a comet is 18 days past its closest approach to the sun, those structures should be ghosts. They should be suggestions. Faint smudges that only show up in long exposure photographs, if you're lucky. 3I Atlas is 17 days past perihelion, and its anti-tail looks like it has been sharpened with a razor blade. If you lined up the images from early November next to this Thailand observation, you would not see decay. You would see intensification. You would see a structure that appears to be organizing itself more tightly, more coherently, as if some mechanism inside or around this comet is actively maintaining it against every dissipative force that should be tearing it apart. And that is where your mind starts asking the questions that keep astronomers awake at night. What kind of particle population could maintain that beam structure? What kind of outgassing pattern could sustain it? What are we actually looking at? Now, before we go further, I need you to understand something. This is not clickbait astronomy. This is not sensationalism dressed up in scientific language. The data is real. The observations are being confirmed by multiple independent sources. The Virtual Telescope project captured similar structures. Michael Yeager documented the anti-tail evolution through October and November. Amateur astronomy networks across Asia, Europe, and the Americas are all seeing the exact same thing. When veteran comet observers, people who have watched hundreds of these objects over decades, start using words like unprecedented and unexpected, you pay attention. Because these are not people who get excited easily. These are people who have seen comets split, flare, and pull off spectacular displays, and they are telling us this one is different. So here is what we are going to do over the next 16 minutes. We are going to investigate this together, not as passive viewers, but as people genuinely trying to understand what is happening above our heads right now. We are going to look at what comets normally do, so you can appreciate why this is genuinely anomalous. We are going to walk through the timeline of 3I Atlas's behavior since it rounded the sun. We are going to examine the competing scientific explanations, because yes, there are natural hypotheses, and we will evaluate each one honestly. We are going to talk about what the December 19th closest approach means for getting answers. And we are going to discuss why this matters beyond just one weird comet. Because 3I Atlas is teaching us that interstellar space is stranger and more diverse than our solar system-centric models assumed. But first, I need to know something. If unexplained cosmic mysteries get your pulse racing, if you are the kind of person who wants to understand the universe at a deeper level than surface headlines allow, hit that like button right now. It tells me you are here for the real investigation, not the simplified version. And drop a comment telling me this. Have you been following 3I Atlas since it first appeared in our inner solar system? Because this story has been building for months, and if you have been watching, you have seen the pattern develop. If you are just joining us now, welcome. You are about to understand why this object has astronomers checking their data 3 times before publishing. Let us start with the foundation, because you cannot appreciate why 3 tails pointing in different directions breaks expectations unless you first understand what should be happening. And once you see the baseline, once you internalize how comets are supposed to behave, the Thailand image transforms from interesting to this changes things. So let me walk you through the physics of comet tails, and then we will come back to why 3I Atlas is rewriting those rules in real time. Think of a comet as a dirty snowball about 10 kilometers across, hurtling through space on an elliptical orbit that brings it close to the sun once every few decades, or in some cases, once every few thousand years. For most of its life, it is frozen solid, a dark lump of ice and rock drifting through the outer solar system, where temperatures hover near absolute zero. But as it falls inward, as the sun's radiation intensifies, something remarkable happens. The ices begin to sublimate. Not melt, sublimate. They go directly from solid to gas, bypassing the liquid phase entirely because there is no atmospheric pressure to maintain liquid water in space. And as those gases escape, they carry dust particles with them, creating a glowing cloud around the nucleus called the coma. And eventually, those magnificent tails that make comets among the most beautiful objects in our night sky. But here is the crucial detail most people do not realize. Comets do not have one tail. They have 2, and those 2 tails form through completely different mechanisms. The ion tail forms when ultraviolet light from the sun strips electrons from gas molecules escaping the nucleus, water vapor, carbon monoxide, carbon dioxide. Those ionized particles become electrically charged, and the solar wind, that constant stream of charged particles blowing outward from the sun at hundreds of kilometers per second, grabs them and drags them directly away from the sun, always directly away. The ion tail is like a windsock pointing straight downwind no matter where the comet is in its orbit. It is typically bluish because ionized carbon monoxide emits light at specific wavelengths that our eyes and cameras perceive as blue, and it is narrow, almost laser-like in some comets, because those ions are being channeled along magnetic field lines embedded in the solar wind. The dust tail is different. Dust particles, microscopic grains of rock and carbon compounds mixed with ice, do not respond to the solar wind. They respond to radiation pressure, the physical push of photons from sunlight. It sounds like science fiction, but photons carry momentum. And when billions of photons per second strike a dust grain, they impart a tiny but real force that pushes the particle away from the sun. But dust particles are heavier than ions. They do not get swept away instantly. They lag behind the nucleus. And because the comet is moving in its orbit, those lagging particles trace out a curved arc. That is why dust tails are broad and curved, following the comet's orbital path like a gentle banner. They are typically yellowish or white because they are reflecting sunlight, not emitting their own light. And they can stretch for millions of kilometers, far longer than ion tails in some cases, because those dust grains just keep drifting outward long after they have left the nucleus. So far, so normal. Two tails, two mechanisms, both well understood. But then there is the anti-tail, and this is where things get optically interesting. An anti-tail is not a third type of tail in terms of physical mechanism. It is a line of sight effect, a geometric illusion that happens when Earth crosses the plane of a comet's orbit. Picture it this way. The comet is shedding dust particles continuously as it moves. Most of those particles spread out into the curved dust tail we can see. But the largest particles, grains a millimeter or more across, sometimes pebble-sized, do not get pushed away as effectively by radiation pressure. They are too massive, so they stay closer to the orbital plane, lagging behind the nucleus, but not swept into the broad tail. When Earth happens to pass through that orbital plane, we are looking edge-on at this thin disk of large particles. And from our perspective, they appear to form a spike pointing back toward the sun, even though they are actually distributed in a flat disk around the orbit. Here is the critical point. Anti-tails are temporary. They peak when Earth crosses the orbital plane, giving us that perfect edge-on view. But within days or weeks, our viewing geometry changes. We drift above or below the plane, and those particles that created the illusion spread out into a broader, fainter structure that blends into the general dust tail or fades into the background of space. The particles themselves are also decelerating without continuous force pushing them. They are subject to tiny perturbations, gravitational tugs from planets, pressure variations in the solar wind, even the faint friction of interplanetary dust. They spread, they disperse. The tight beam structure dissolves. In 99% of comets, anti-tails are visible for maybe 2 weeks at most. And that is being generous. By the time you are 2 or 3 weeks past perihelion, especially if the comet is moving away from the sun, those structures should be archaeological remnants, not active features. Think of it like watching dust settle after an explosion. In the first few seconds, you might see defined beams or jets where the force was directed, but give it time, and turbulence and gravity take over. The dust spreads, the pattern blurs. You do not see a sharp beam an hour later unless something is actively maintaining it. And in the case of comets, once perihelion is passed, once the peak heating is over, there is no mechanism that should actively maintain an anti-tail. The outgassing is decreasing, the particle production is dropping. The existing particles are spreading out. Everything about post-perihelion physics says the anti-tail should fade. So when 3I Atlas passed perihelion on October 29th, astronomers expected to see exactly that pattern. They expected the anti-tail that had been observed in late September and early October would peak around perihelion, maybe linger for a week or so, and then dissolve as the comet moved away from the Sun and Earth's viewing angle changed. They expected the standard two-tail configuration to dominate, ion and dust, with the anti-tail becoming a memory that only shows up if you dig through archived images and process them heavily. That is not pessimism. That is not a lack of imagination. That is pattern recognition based on centuries of cometary observations. We have watched thousands of comets. We know what happens after perihelion. The show winds down. The tails retract. The comet fades as it climbs back out toward the outer solar system. 3I Atlas did not follow the script. And that is where our story takes a turn from textbook predictability into genuine scientific mystery. Because when astronomers pointed their telescopes at this object in early November, expecting to document its predicted fade, they found something that made them check their calibrations, verify their timestamps, and quietly start reaching out to colleagues asking, "Are you seeing this too?" Keep this baseline in mind: the normal behavior, the expected timeline, the physics that governs 99% of comets. Because what we are about to walk through is the 1% case that makes scientists rethink their models. And it all starts with a series of observations that progressively violated every checkpoint on the expected timeline. Let us go back to September. 3I Atlas is inbound, approaching the Sun, and astronomers are documenting its behavior as it enters the inner solar system. Michael Yeager and other experienced comet observers start noticing the anti-tail developing. This is expected. Earth is approaching the crossing point of the comet's orbital plane, and the viewing geometry is setting up perfectly to see that edge-on disk of large particles. Images from mid to late September show a clear anti-tail structure, a spike extending sunward from the nucleus exactly as predicted. Nothing anomalous yet. This is textbook. Observers are documenting it, measuring it, preparing for what they expect will be a spectacular display around perihelion, followed by the standard fade. October 29th arrives. Perihelion, the moment of closest approach to the Sun. This is when the comet experiences maximum solar heating, maximum sublimation, maximum activity. And here is where the first surprise happens. Though it is subtle enough that it does not trigger alarm, the comet survives intact. Now, you might think, of course it survives. Comets survive perihelion all the time. And you would be right. But there had been some speculation based on 3I Atlas's brightness and activity patterns that it might fragment or split during perihelion passage. Some comets do. The thermal stress, the rapid sublimation, the structural weaknesses in the nucleus. They can cause breakup. 3I Atlas did not fragment. It came through perihelion as a single coherent object, which is good news for observers because it means there is still something to study. But it also means the nucleus is either more robust or more cohesive than some early models suggested. Now we move into early November, and this is where the timeline starts deviating from expectations. November 1st, November 5th, November 10th. Multiple observers across different continents are imaging 3I Atlas as it moves away from the Sun. and the anti-tail is still there. Not just present, but prominent. Images from the first week of November show a structure that has not noticeably weakened. Some observers comment that it looks about as sharp as it did pre-perihelion, which is unusual, but not yet alarm-inducing. Maybe the particle population is larger than normal. Maybe the viewing geometry is just exceptionally favorable. There are always small variations between comets, but as we push deeper into November, as we get to day 10, day 12, day 15 post-perihelion, the expected fading is not happening. November 10th, the Virtual Telescope project run by Gianluca Massi in Italy captures a stunning image of 3I Atlas showing all three tail structures clearly defined. The ion tail is streaming away from the sun, textbook perfect. The dust tail is forming its characteristic curve, and that antitail is still there, sharp and linear, like someone drew it with a straight edge. Massi's commentary notes the unusual persistence. Other observers start comparing their images, and a quiet conversation begins in astronomy forums and email lists. Is anyone else seeing this? How long is this anti-tail going to last? Has anyone seen persistence like this before in other comets? The answers are variations on a theme. This is longer than usual. This is sharper than expected. And no, most comets do not maintain this kind of structure this far past perihelion. Then we get to November 13th through the 15th. And this is when the Thailand observations come in. Tiasak Talawang is imaging from Rayong with a 0.26-meter telescope. The viewing conditions are excellent. The image processing brings out detail that makes veteran observers stop scrolling. Because what is in these images isn't just persistence, it is intensification. The antitail does not look like it is fading. It looks, if anything, more defined than it was 2 weeks earlier. The boundaries are sharp. The structure is coherent, and it is extending farther from the nucleus than some earlier observations showed. You can pull up the September images and compare them side by side with the November 15th Thailand image. And your brain rebels against what you are seeing because the physics says this should be moving in the other direction. Fainter, more diffuse, blending into the background, not sharper, not stronger. Let us contextualize this with numbers, not because the exact figures matter for our discussion, but because they illustrate the time scale. We are just over 2 weeks past perihelion when those Thailand images are captured. 18 days is an eternity in cometary timescales for anti-tail persistence. Most documented well-studied comets fade significantly within 1 week. They are barely detectable by 2 weeks. By 18 days, you would need heavy image processing and long exposures to even hint at the structure. 3I Atlas's anti-tail is showing up in moderate exposure images without extreme processing. That is not a subtle anomaly. That is a screaming data point that says something fundamentally different is happening here. And here is where pattern recognition becomes critical. In every previous interstellar object we have studied, and admittedly we have only confirmed 2 before 3I Atlas, we have seen behavior that mostly fits our models with some variations. 2I Borisov, the other interstellar comet, behaved largely as expected. It had unusual composition, yes, different ratios of certain molecules, but its tail structures followed the standard playbook. It did not maintain anti-tails beyond normal timescales. It did not show persistent structures that violated decay predictions. 3I Atlas is charting new territory. And the frustrating, fascinating thing is that each checkpoint where we expected the behavior to normalize, 1 week post-perihelion, 2 weeks, 18 days, has instead shown continued anomaly. Astronomers are now comparing 3I Atlas's anti-tail persistence to some of the most complex comets on record. Comet Hale-Bopp in the late 90s showed multiple tail structures and complex activity, but even Hale-Bopp's features followed predictable evolution. By equivalent post-perihelion stages, its structures were calming, not intensifying. Comet Holmes, which underwent a dramatic outburst and created a massive coma, still followed dust dynamics that made sense within weeks. We can point to unusual comets throughout history, and they all eventually conform to the physics of particle dispersion and decay. 3I Atlas is now at a point where it should be conforming, and it is not. That is what has the scientific community's attention. Not that it is unusual. Unusual comets happen. But that it is staying unusual past the point where unusual typically fades. So, we arrive at mid-November with a situation that demands explanation. 3 tails, all clearly defined. An antitail that has maintained structure for at least 3 weeks and possibly intensified. Observations from multiple independent sources confirming the same pattern, and a growing realization that whatever model we apply to explain this, it has to account for sustained structure against dissipative forces that should have erased it by now. The timeline itself is the evidence. Each date is a data point. And when you plot those points, you do not get the downward curve of fading activity. You get a flat line, or possibly an upward trend, depending on how you measure sharpness and extent. That is the anomaly. That is what we are investigating. And that brings us directly to the observations that sparked the current wave of attention. Because the Thailand images are not just confirmation of what was already known. They are the clearest, sharpest documentation yet of a structure that should not be this prominent this long after perihelion. The 0.26-meter telescope in Rayong, Thailand, is not one of the giants. It is not Hubble. It is not the European Southern Observatory's very large telescope, but it has something those facilities sometimes do not have: time and dedication from an observer who has been tracking 3I Atlas consistently. Tiasak Talawang operates this instrument, and on the nights of November 13th through the 15th, viewing conditions aligned perfectly. Clear skies, low light pollution in the observing direction, the comet positioned at a favorable altitude above the horizon. And what came through in those images is the kind of detail that makes you realize why ground-based amateur astronomy still contributes meaningfully to professional research. The 3-tail structure is immediately obvious. You do not need to be an expert to see it. The ion tail extends upward in the frame, a thin bluish streamer that is being dragged directly away from the sun by solar wind. You can see its characteristic straightness, the way it maintains a narrow column even as it stretches across the field of view. The dust tail arcs to the side, broader and more diffuse, reflecting sunlight with that yellowish-white glow that comes from small particles scattering light in all directions. It curves gently, following the comet's orbital motion exactly as radiation pressure physics predicts. And then there is the antitail, pointing in the opposite direction from the ion tail, aiming back toward the sun, a sharp linear feature that looks almost artificial in how well-defined it is. But here is what makes these Thailand observations particularly valuable, beyond just the image quality. The viewing geometry from Thailand's latitude provides a slightly different perspective than European or North American observations from the same nights. Parallax is not a factor over these distances. The comet is far enough away that observers on Earth see essentially the same view. But atmospheric conditions, local light pollution, and the angle above the horizon all affect image quality. Thailand's tropical latitude meant 3I Atlas was higher in the sky, passing through less atmospheric mass, which reduces distortion and light scattering. That translates to sharper images, better detail in the tail structures. And what that detail reveals is structure within the antitail itself. Look closely at the processed images, and you can see that the antitail is not perfectly uniform. There are brightness variations along its length, subtle but real. Some sections appear slightly brighter, suggesting denser concentrations of particles. The edges, where the antitail meets the background sky, are remarkably sharp. This is important because diffuse structures, clouds of particles spreading out randomly, do not have sharp edges. They fade gradually into the background. Sharp edges suggest collimation, a focusing mechanism, something that is keeping particles confined to a relatively narrow beam instead of letting them spread out spherically. That is what is so visually striking about these images. The antitail looks organized. It looks like there is structure being maintained against the natural tendency of particles to disperse. Now, let us talk about what astronomers expected to see in mid-November versus what these images show. The expectation was simple. By 18 days post-perihelion, any antitail structure should be a faint remnant, possibly requiring long exposures and heavy processing to detect. The ion and dust tails would be prominent. Those are sustained by ongoing activity as the nucleus continues to outgas, even while moving away from the sun. But the antitail, that geometrical artifact of large particles in the orbital plane, should be fading into obscurity. What the Thailand images show instead is an antitail that dominates the visual frame almost as much as the other two tails. It is not an afterthought. It is not something you have to squint to see. It is there, bold and obvious, demanding explanation. Comparative analysis with earlier observations makes this even more striking. Pull up Michael Yeager's images from late October, right around perihelion. The antitail is present, clearly defined, exactly as expected for that stage. Now jump to the Virtual Telescope Project's November 10th image. Still present, still sharp, but maybe you can argue it is about the same brightness as perihelion. Now look at Thailand's November 15th images. The antitail has not weakened. If you compare brightness profiles, measurements of how much light is coming from different parts of the tail, the antitail in mid-November is comparable to, or possibly brighter than it was at perihelion. That is the data point that makes astronomers pause, because brightness in a tail structure correlates with either particle density or particle size. Either there are more particles in the antitail now than there were at perihelion, which implies ongoing production, or the particles are larger and reflecting more light, which raises questions about where those large particles are coming from this far past peak activity. Expert reactions have been measured but clearly intrigued. Gianluca Massi commented on the remarkable persistence of the structure. Michael Yeager's observing logs note the unexpected continuation. Avi Loeb, the Harvard astrophysicist who has become known for asking uncomfortable questions about unusual objects, published a Medium article on November 16th specifically addressing 3I Atlas's antitail and raising the possibility that conventional explanations might be insufficient. We will dig into the competing theories in a moment, but the point here is that this is not fringe speculation. This is mainstream astronomical observation yielding results that do not fit the standard template. And people who have spent careers studying comets are saying this is unusual enough to warrant deeper investigation. There is also the context of what these images represent in terms of observational capability. We are living in an era where amateur astronomers with modest equipment can capture data quality that would have required professional observatories a few decades ago. CCD cameras, advanced image processing software, automated tracking mounts. These tools have democratized astronomy to the point where a dedicated observer in Thailand can contribute images that professional researchers cite in their analysis. The Thailand observations are not just pretty pictures. They are scientific data, time-stamped and calibrated, showing a phenomenon that challenges our models. And they are part of a larger network of observations from around the world, all confirming the same basic fact. 3i Atlas is maintaining a triple-tail structure well past the point where theory says it should have simplified to the standard two-tail configuration. So we are left with this image, this impossible persistence, and a fundamental question that cannot be avoided. If natural processes fully explain this, what specific mechanism is producing sustained anti-tail structure 18+ days post-perihelion? What particle population? What size distribution? What ongoing activity pattern could account for this? And if natural processes do not fully explain it, if we are missing something in our models, what are we missing? Those questions drive us directly into the competing hypotheses, because science does not leave mysteries sitting unanswered. Science builds explanations, tests them against data, refines or discards them based on evidence. And right now, there are three main natural explanations being discussed, each with strengths and each with problems. Let us examine them honestly, one by one, because understanding where the conventional explanations struggle is how we appreciate the depth of this mystery. Theory 1. Massive dust grain population. This is the most conservative explanation, the one that stays closest to known physics without invoking anything exotic. The idea is straightforward. If 3i Atlas shed an unusually large quantity of massive dust grains, particles a millimeter or more in diameter, perhaps even pebble-sized, during its approach to perihelion, those particles would be too heavy for radiation pressure to push away quickly. They would stay close to the orbital plane, creating that anti-tail appearance. And because they are massive, they would take longer to spread out. Gravitational perturbations and solar wind pressure would still affect them, but more slowly than smaller dust grains. So the persistence we are seeing could be explained by the sheer volume and mass of the particle population. There are just so many large particles that even 18 days of dispersion have not thinned them below detectability. This theory has merit. It does not require new physics. It does not invoke exotic processes. It just requires that 3i Atlas produced more particles than typical comets. And there is precedent for comets showing unusual dust production. Some comets are dustier than others, with higher ratios of solid particles to gas. If 3i Atlas has an internal structure that fragments easily, or if its approach to the Sun triggered more extensive breakup of surface layers, it could have released a substantial cloud of millimeter-scale and larger debris. That debris would form exactly the kind of flat disk we are observing, and its longevity could be explained by mass and quantity. But here is the problem: the sharpness. If we are looking at a massive population of large particles spreading out over 18 days, we would expect to see blurring. We would expect the anti-tail to be widening, the edges becoming more diffuse as individual particles drift at slightly different velocities and angles. Instead, the Thailand images show boundaries. The anti-tail maintains a relatively narrow profile. That suggests either the particles are being replenished, new large particles are being added continuously to replace ones that drift away, or there is some focusing mechanism keeping them collimated. Continuous replenishment this far past perihelion is hard to justify. Comet activity drops off as you move away from the Sun. Sublimation decreases. particle production should be declining, not maintaining a steady output of large grains. And as for a focusing mechanism, radiation pressure pushes particles away. It does not focus them. There is no known natural process that would collimate a beam of millimeter-scale particles in this configuration. So Theory 1 explains some of what we see, the persistence, but struggles with the sharpness and the apparent non-dispersion of the structure. It is not impossible. It could be that viewing geometry is coincidentally hiding the dispersion, that we are seeing a projection that makes spread look narrower than it is. But that requires fortunate angles that seem unlikely given how long this has persisted. Let us move to Theory 2. Theory 2: icy fragmentation and subnuclei. This hypothesis suggests that 3I Atlas's nucleus broke apart, either during perihelion or shortly after, producing large icy fragments. Chunks of the original nucleus ranging from meters to possibly kilometers across. These fragments would act as temporary mini-comets, each one sublimating and producing its own small coma and tail. But because they are close together, having just separated from the parent body, their individual outgassing plumes could interact and create complex tail structures. The antitail in this model would be sustained by ongoing sublimation from these fragments as they slowly separate and drift along the comet's orbit. This theory also has precedent. Comets do break apart. We have observed fragmentation events, and the resulting debris fields can be spectacular. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before impacting Jupiter. Comet Schwarzmann-Wachmann 3 split into dozens of pieces during its 2006 apparition. Fragmentation can produce complex structures, and if the fragments are large enough and icy enough, they can remain active for extended periods, creating tails that overlap and merge from our perspective. So if 3I Atlas broke into several large pieces, each piece outgassing independently, that could create a complex tail morphology, including structures that point in unusual directions depending on the viewing geometry and the individual fragment orbits. But again, we run into problems. First, we do not have direct evidence of fragmentation. Observers have been monitoring 3I Atlas closely, and while the nucleus is not resolved as a disk, it is too far away and too small for that, we can measure the central brightness concentration. If the nucleus had split into multiple fragments, we would expect to see multiple brightness peaks in high-resolution images, or at least an elongation of the central condensation. The observations show a single compact nucleus. That does not rule out fragmentation completely. Small fragments could be too faint to detect individually, but it makes large-scale breakup less likely. Second, the sharpness problem persists. If we are looking at outgassing from multiple fragments, we would expect irregularities, patchiness, variations in brightness and structure. As different fragments contribute different amounts of material at different times, the antitail looks smooth and continuous, not like a composite of several sources. There is also a timing issue. If fragmentation happened at or near perihelion, we would expect the fragment separation to be increasing over time as each piece follows a slightly different orbit. That increasing separation should make the tail structures more complex and chaotic, not sharper and more organized. The fact that the antitail maintains coherence suggests either the fragments are still very close together, moving in almost identical orbits, which is possible for the first few days but becomes less likely over weeks, or there is no fragmentation, and we are looking at a single nucleus producing this structure through some other mechanism. Theory 3: directed jets from stable vents. This is perhaps the most interesting conventional explanation because it invokes a mechanism we know exists in comets, but rarely see so persistently. The idea is that 3I Atlas's nucleus has one or more active regions, vents, or fractures that are producing focused jets of gas and dust. If these jets are oriented such that they eject material in a relatively narrow cone, and if the nucleus rotation is slow or the vent is located near a rotation pole, the jet could remain pointed in roughly the same direction for extended periods. The anti-tail in this model is a sustained jet that happens to point sunward from our viewing angle. It is not an optical illusion of lagging particles. It is active, ongoing outgassing from a specific location on the nucleus. Jets are real. We have seen them on many comets. The Rosetta mission to Comet Churyumov-Gerasimenko directly imaged jets erupting from the nuclear surface. Some of them were quite collimated and persistent. Jets form when subsurface ice is heated unevenly, creating pressure that ruptures the surface in localized spots. Once a vent opens, it can remain active as long as there is ice beneath it to sublimate. And if the vent is narrow and the gas pressure high, the jet can be tightly focused, creating a beam-like structure rather than a diffuse cloud. So the physics is sound. Jets can create sharp features. They can be sustained over weeks if the vent remains active, and they can point in directions that seem unusual depending on the nucleus orientation and our viewing geometry. The challenge with this theory is rotational smearing. Comets spin. Comet nuclei typically have rotation periods ranging from hours to days. As the nucleus spins, any fixed vent on its surface would sweep through a circle like a lighthouse beam. From our perspective, we would see the jet appear, brighten as it rotates toward us, then fade as it rotates away. Over multiple rotations, this would create a fan-shaped or conical structure in the tail, not a narrow beam. For a jet to create a persistent, sharp linear feature like the anti-tail, the nucleus would have to be rotating very slowly. So slowly that the jet's direction does not change much over the weeks we have been observing. Or the vent would have to be located at the rotation pole aligned with the spin axis, so it always points in the same direction regardless of rotation. Both scenarios are possible, but statistically unlikely. Slow rotation is not unheard of, but most comets spin relatively fast because they have been gravitationally stirred by planetary encounters over millions of years. And having a vent precisely at the pole in an orientation that happens to create a sunward-pointing jet at this specific moment is a fortunate coincidence. It is not impossible. Coincidences happen. But when you are stacking coincidences, unusual composition, convenient vent location, fortuitous viewing geometry, extended activity, the explanation starts feeling contrived. It could be true. The data does not rule it out, but it is not satisfying in the way a robust explanation should be. So we have three natural explanations, each explaining some aspects of the observations, but struggling with others. The massive dust grain theory explains persistence, but not sharpness. The fragmentation theory explains complexity, but lacks evidence of breakup, and does not explain coherence. The directed jet theory explains focus, but requires unlikely geometry. This is where science gets messy and interesting, because when the standard models do not fully fit, you have two options. Option 1. Refine the models, combine elements, propose hybrid scenarios. Maybe it is large dust grains and directed jets. Maybe it is fragmentation producing a few large pieces, one of which has a particularly active vent. These hybrid explanations can work, but they add complexity. And there is a principle in science, Occam's razor, that simpler explanations are generally more likely than complex ones, all else being equal. Option 2. Consider whether there is something about 3I Atlas's origin that makes conventional models insufficient. And this is where the interstellar factor becomes critical, because 3I Atlas did not form in our solar system. It formed in an entirely different stellar environment, potentially billions of kilometers from a different star under conditions that might have been radically different from the nebula that birthed our Sun and planets. And if its composition is exotic relative to solar system comets, if it contains ices and materials we rarely encounter, its behavior might be exotic too. That is not speculation for the sake of drama. That is a scientifically valid consideration, because understanding where 3I Atlas came from and what that might mean for its makeup is essential to evaluating whether our conventional theories are even applicable. When 3I Atlas was first identified as interstellar, confirmed through its hyperbolic orbit that traces back to origins outside our solar system, it became the third verified visitor from the vast space between stars. The first was Oumuamua, that mysterious elongated object that tumbled through our inner solar system in late 2017, moving too fast and too strangely to have originated from the Sun's gravitational influence. The second was 2I Borisov, a more conventional-looking comet that appeared in 2019 and behaved mostly as we would expect a comet to behave, with the key difference that its trajectory confirmed it came from elsewhere. And now 3I Atlas arriving in 2025, showing us that interstellar objects are more common than we once thought, and more diverse than a sample size of 3 can fully capture. But here is what makes the interstellar origin so significant for this investigation. Comets born in our solar system formed roughly 4.6 billion years ago from the same cloud of gas and dust that collapsed to form the Sun and planets. We call it the solar nebula. The composition of that nebula was determined by the specific mix of elements present in this region of the galaxy at that time. Hydrogen, helium, oxygen, carbon, nitrogen, traces of heavier elements, all in proportions that we can measure in meteorites, in planetary atmospheres, in comets themselves. Our solar system's comets are chemical fossils from that epoch, and their ices reflect the conditions of the outer solar nebula where they formed. Water ice dominates, with mixtures of carbon dioxide, carbon monoxide, methane, ammonia, and more exotic molecules in smaller quantities. 3I Atlas formed in a different nebula, orbiting a different star. We do not know which star. Its trajectory does not trace back clearly to any nearby stellar system, which means it has been wandering interstellar space for potentially millions of years after being ejected from its birth system by gravitational interactions with planets. But wherever it formed, the conditions were different. The stellar nebula around its parent star had a different composition, different temperatures, different dynamics. And that means 3I Atlas's internal makeup could be significantly different from the comets we have studied for centuries. It might have ices we rarely see. It might have dust grains with unusual mineralogy. It might have structural properties, porosity, layering, cohesion, that differ from the comets we are accustomed to. Previous spectroscopic observations of 3I Atlas, conducted by Hubble and by ground-based observatories with spectrographs, detected carbon-based molecules in its coma. Specifically, they found evidence of molecular carbon chains and possibly carbon monoxide in higher abundances than typical for solar system comets. Carbon monoxide is interesting because it is a volatile ice. It sublimates at much lower temperatures than water. Water ice needs to be warmed to about 200 Kelvin before it starts sublimating significantly. Carbon monoxide starts sublimating below 100 Kelvin. If 3I Atlas formed in an exceptionally cold region of its natal stellar system, think of the outermost reaches 100 or more astronomical units from its parent star. It could have incorporated large amounts of carbon monoxide and other super-volatile ices that solar system comets do not contain in such abundance. Why does this matter for the antitail mystery? Because super-volatile ices change the activity profile. A comet rich in carbon monoxide would start outgassing much farther from the Sun than a water-dominated comet. It would remain active longer as it moves away from the Sun because those volatiles continue sublimating even at lower temperatures. And the gas pressures generated by sublimating carbon monoxide are different from water, which affects how dust particles are ejected and accelerated. If 3I Atlas has a core rich in carbon monoxide ice, it could be producing sustained outgassing even now, just over 2 weeks past perihelion, at a level that water-dominated comets would not sustain. That ongoing outgassing could be feeding the antitail, replenishing particles, maintaining structure against dispersion. There is also the dust composition question. Spectroscopy does not just tell us about gases. It can reveal information about the solid particles in the coma and tails based on how they scatter and absorb light at different wavelengths. Some early analyses of 3I Atlas's dust suggest it might be carbon-rich. More organic material, less silicate rock than typical solar system comets. Carbon-rich dust behaves differently under radiation pressure. It absorbs light differently, reflects differently, and its thermal properties affect how quickly particles cool or heat as they move through space. If the antitail particles are composed of unusual carbon compounds, they might be cohering differently, clumping into larger aggregates, or maintaining density through some process we do not fully understand because we have never studied this exact material before. So the exotic composition hypothesis is compelling. It does not require abandoning known physics. It just requires acknowledging that the material inventory of 3I Atlas might be outside the range we have thoroughly characterized. Our models of cometary behavior are built on thousands of observations, but those observations are all of solar system comets. We have studied exactly 2 interstellar comets in detail before this one. And 2I Borisov, while chemically interesting, was too faint during most of its apparition to provide the level of detail we are getting from 3I Atlas. We are essentially building a new category of knowledge, and 3I Atlas is only the 3rd data point. Drawing broad conclusions from 3 examples is risky, but so is assuming our solar system-based models apply universally. But, and this is critical, even exotic composition has limits. Super volatile ices can explain sustained activity. Unusual dust can explain some optical properties. But can they explain the sharpness and persistence of the antitail structure against 18 days of dispersion? Can carbon monoxide outgassing alone maintain a collimated beam of particles when radiation pressure, solar wind turbulence, and orbital mechanics are all trying to spread them out? This is where even the exotic composition theory runs into the same problem as the conventional theories. It provides a mechanism for ongoing activity, which is good. But activity alone does not guarantee structure. You need a focusing mechanism, a reason why the particles stay in a narrow beam rather than puffing out in all directions like they do in the broader dust tail. And that brings us to the uncomfortable edge of this investigation. The point where natural explanations, while possible, require stacking assumptions and fortunate circumstances to fully account for the observations. It is not that any single assumption is unreasonable. Large particles exist, jets exist, exotic ices exist. But when you need all of them together in specific configurations at specific times to explain one feature of one comet, the explanation starts feeling less like a robust model and more like a tailored fit. And that is when scientists start asking the next level question, not because they want to abandon natural explanations, but because intellectual honesty requires considering all possibilities when the standard models struggle. This is where Avi Loeb's commentary comes in, and it is important to frame this correctly. Loeb is a tenured professor of astronomy at Harvard, former chair of the astronomy department, with a research career spanning black holes, cosmology, and high-energy astrophysics. He is not a fringe figure. He has also become known in recent years for publicly advocating that the scientific community should be more open to considering non-natural explanations for anomalous objects, particularly in the context of Oumuamua, which he has argued could have been artificial rather than a comet or asteroid. His position is controversial, and most astronomers disagree with his specific claims about Oumuamua. But his broader point that science should follow evidence even when it leads to uncomfortable conclusions is philosophically sound. In his November 16th Medium article about 3I Atlas, Loeb points out that if the antitails particles are moving at velocities significantly higher than what natural degassing can produce, that would require an explanation beyond sublimation pressure. Natural outgassing from comets accelerates particles to speeds of a few hundred meters per second, sometimes up to a kilometer per second in very active jets. If spectroscopy measures velocities in the range of multiple kilometers per second, that starts looking less like gas pressure and more like something else. Loeb suggests cautiously that one possibility worth investigating is whether the velocity could be explained by artificial propulsion, a directed energy source. Essentially, he is not claiming this is the answer. He is saying it is a hypothesis that should be testable through velocity measurements, and science should be willing to test it. Most astronomers hearing this will immediately focus on the natural explanations, and rightly so. Extraordinary claims require extraordinary evidence, and the evidence for artificial origin would need to be far more compelling than the anti-tail is persistent. But here is the value of Loeb's position. It highlights that we do not yet have the data to definitively rule anything out. We have images, we have morphology, we have some spectroscopy, but we do not have precise velocity measurements of the anti-tail particles. We do not have high-resolution spectroscopy of the nucleus itself. We do not have the observational detail that would let us say, with confidence, yes, this is explained by mechanism X, and we can rule out mechanisms Y and Z. And until we have that data, the scientifically appropriate stance is to hold multiple hypotheses loosely, favoring natural explanations, but not closing the door on questions that could be answered through better observations. So where does that leave us? With an interstellar comet whose exotic origin provides plausible mechanisms for unusual behavior, but whose specific anti-tail characteristics still push the boundaries of what those mechanisms can easily explain. With natural theories that are viable but not fully satisfying, and with the awareness that better data is coming. Data that could settle this question definitively. The December 19th close approach is not just a milestone for observers hoping for pretty pictures. It is a scientific opportunity to gather measurements that could distinguish between competing explanations. And that is where our attention turns next. Because the observations planned for late December and the data they will produce are the key to moving from mystery to understanding. December 19th, 2025. Mark that date because it represents the optimal observation window for 3I Atlas. On that date, the comet makes its closest approach to Earth, about 1.8 astronomical units, roughly 270 million kilometers. That is not close by inner solar system standards. It is farther than Mars at its closest to Earth. But in astronomical terms, it is close enough to matter, because every kilometer of distance affects the resolution and signal strength of the observations we can make. And between now and that date, every major telescope that can be scheduled, every observatory with time allocation available, is being tasked with looking at this object. The priority is spectroscopy, high-resolution spectroscopy, specifically designed to measure the velocities of particles in the antitail and the other tail structures. Here is how that works. When particles move, their light gets Doppler shifted. If they are moving toward us, the light shifts slightly bluer, higher frequency. If they are moving away from us, it shifts redder, lower frequency. By taking a spectrum of the comet's tails and analyzing the precise wavelengths of emission lines from ions and reflected light from dust, astronomers can calculate how fast those particles are moving and in what direction. This is not a rough estimate. With good spectrographs, you can measure velocities to within tens or hundreds of meters per second. That precision is enough to distinguish between natural outgassing, which accelerates particles to maybe half a kilometer per second, and something more energetic. If the spectroscopy shows that anti-tail particles are moving at speeds consistent with sublimation pressure, that strongly supports the natural explanations. It would mean the particles were ejected by gas pressure from the nucleus and are now coasting, gradually slowing due to radiation pressure and spreading due to velocity dispersion. That is the expected result, and it would point toward the exotic ice hypothesis or the massive particle population theory as the most likely explanation. The mystery would not be completely solved. We would still need to understand why the structure is so sharp, but it would narrow the field significantly. If the spectroscopy shows higher velocities, velocities that cannot be explained by gas pressure alone, that opens new questions. What mechanism is accelerating those particles? Radiation pressure is always present, but it is a gentle force, not sudden acceleration. Solar wind can transfer momentum. But again, the accelerations are gradual. If particles are moving significantly faster than sublimation plus radiation pressure can account for, you would need an additional energy source. That does not immediately mean artificial. It could mean an internal process we have not fully understood. Perhaps electrostatic charging and repulsion, where particles build up electric charge from solar UV and repel each other, gaining velocity. That is a known phenomenon on airless bodies. Or it could mean jets with higher than expected gas velocities due to some unusual thermal process in the nucleus. The point is, anomalous velocities would require a deeper level of investigation, and they justify more exotic hypotheses being taken seriously. Beyond spectroscopy, there is photometry, measuring brightness changes over time. If the antitail brightens, dims, or shows periodic variations, that tells us about the particle production rate and possibly the nucleus rotation. A brightening antitail would suggest increasing activity, which would be even more anomalous because activity should be decreasing as the comet moves away from the sun. A dimming antitail would finally match expectations and suggest the persistence we have seen is reaching its limit. Periodic variations, if they match a rotation period, would support the directed jet hypothesis, showing that the jet rotates with the nucleus, and we are seeing brightness cycles as it points toward and away from us. Morphological tracking is also critical. High-resolution imaging through late November and December will map how the antitail structure evolves day by day. Does it maintain its sharp profile, or does it start to blur and widen? Does it break into filaments or segments, which would suggest particle streams with different velocities? Does it remain straight, or does it curve, which would reveal the orbital mechanics of the particles more clearly? These are questions that time series imaging will answer, and each answer constrains the possible explanations. Structure that maintains coherence over weeks, despite all the forces trying to disperse it, suggests something actively maintaining it. Structure that finally starts to break down in December would suggest we have been watching the slow decay of a large particle cloud, and the persistence was just a matter of volume and mass overwhelming dispersion rates. Multi-wavelength observations add another layer. Looking at the comet in radio wavelengths can detect specific molecules like carbon monoxide and methanol that emit radio photons when they are excited by sunlight. Infrared observations reveal thermal emission from dust grains, telling us about their temperature and composition. Ultraviolet observations highlight ion populations and can map the solar-wind interaction. Each wavelength provides a different piece of the puzzle, and together they build a comprehensive picture of what is happening. If radio observations show strong carbon monoxide emission from the direction of the anti-tail, that supports ongoing sublimation of volatile ices feeding the structure. If they do not, that suggests the anti-tail is primarily dust, and the particles were ejected earlier and are now just coasting. The observatories participating in this campaign include the European Southern Observatory's Very Large Telescope, which has some of the best spectrographs in the world. Ground-based networks like the Las Cumbres Observatory, which has telescopes around the globe that can track the comet continuously. Space-based platforms like Hubble, if observing time is allocated. Hubble's schedule is heavily booked, but interstellar objects often get priority given their rarity. Even smaller observatories and amateur networks are contributing imaging data, providing continuous monitoring that helps identify short-term changes or outbursts. This is a coordinated effort, and the data is being shared in near real time through astronomical telegrams and circulars so that observers worldwide can refine their strategies based on what others are seeing. December 19th is the peak, but the observation window extends from now through early January. By mid-December, preliminary results from spectroscopy should start appearing in astronomers' telegrams. Brief announcements that share key findings before full papers are written. By early January, enough data will have been analyzed to start drawing firm conclusions. And by late January or February, expect to see papers submitted to journals presenting comprehensive analysis of 3I Atlas's behavior during this apparition. That timeline means we are weeks away from having answers, not months. The scientific process is moving quickly because the target is time-sensitive. Comets fade as they move away from the sun, and the opportunity to gather high-quality data is limited. What each outcome would mean is worth considering. If the data confirms natural processes, exotic ices, large particles, sustained jets, 3I Atlas becomes a case study in the diversity of interstellar objects, and a reminder that our models need to accommodate wider ranges of composition and behavior. That is valuable. It refines our understanding. It improves our ability to predict and interpret future interstellar visitors. If the data reveals something that does not fit current natural models, if velocities or structures defy known mechanisms, then the scientific conversation shifts. More exotic natural processes would be proposed and tested. And if those still do not suffice, the door opens to truly novel explanations, which would be extraordinary, but also extraordinarily exciting because they would mean we are learning something fundamentally new about how the universe works. So the upcoming observations are not just about 3I Atlas. They are about how science investigates mysteries. They are about the process of gathering evidence, testing hypotheses, and refining understanding. And they are a demonstration that we live in an era where these investigations happen in real time, where dedicated observers and professional researchers collaborate globally, and where interested people like you can follow along as discoveries unfold. This is not a mystery that will be solved in secret and announced years later. This is science happening now, and the next 4 weeks are the critical window. Which brings us to the broader context, because 3I Atlas is one object, but it represents the beginning of a new field in astronomy, the study of interstellar objects as a population, not as individual curiosities. And that is a shift in perspective that matters for how we think about our place in the cosmos. When Oumuamua raced through our inner solar system in October 2017, it was the first confirmed interstellar object humanity had ever detected. Before that moment, interstellar visitors were theoretical. We knew they had to exist. Stellar systems form with far more comets and asteroids than they retain, and gravitational interactions eject countless objects into the void between stars. Calculations suggested that interstellar space should be filled with wandering debris from billions of star systems, a sparse but vast population of rogue worlds, comets, asteroids, all drifting through the galaxy, unbound to any star. But theory is one thing, detection is another. And until Oumuamua, we had never seen one. Oumuamua was a shock for multiple reasons. Its shape appeared elongated, possibly cigar-like or pancake-like, depending on interpretation. Its light curve, the way its brightness changed as it tumbled, was unlike any asteroid or comet previously observed, and it exhibited a small but measurable non-gravitational acceleration, a tiny push that could not be fully explained by solar radiation pressure alone. That acceleration sparked the debate that continues today, with most scientists attributing it to outgassing from volatile ices, turning Oumuamua into a comet, even though it showed no visible tail, and a minority, including Avi Loeb, arguing that the data is consistent with artificial origin, perhaps a light sail or debris from alien technology. The debate is not settled, and it probably will not be unless we detect another object with similar characteristics and can study it more thoroughly. 2I Borisov arrived in August 2019, and it was different from Oumuamua in almost every way. It looked like a comet, visible coma, clear tail, behavior that matched cometary models reasonably well. Its chemistry was unusual in some respects, with different ratios of carbon monoxide to water than solar system comets typically show, but not so unusual that it defied explanation. 2I Borisov became the proof of concept that interstellar comets exist and that they can be studied with the same tools we use for solar system comets. But it was faint throughout most of its passage, limiting the detail we could extract. High-resolution spectroscopy was challenging. Nucleus imaging was impossible. It remained a point source. We learned, but we were still data-limited. 3I Atlas arriving in 2025 is the third confirmed interstellar object, and it is providing a level of observational detail we did not get from the first two. It is bright enough to study spectroscopically. It is active enough to show clear tail structures. Its trajectory brought it through the inner solar system at an angle and timing that gives us months of observing opportunity, not just a few weeks. In many ways, 3I Atlas is the ideal interstellar object for study. Bright, active, well-positioned, and displaying behavior that is unusual enough to teach us something new without being so bizarre that we cannot make sense of it at all. What 3I Atlas is teaching us goes beyond its specific anti-tail mystery. It is teaching us that interstellar objects are diverse. 3 objects, 3 very different presentations. Oumuamua was inert, or nearly so, with no obvious tail, possibly rocky or possibly icy, but with volatiles that sublimate without visible dust. 2I Borisov was a relatively standard comet, chemically interesting but behaviorally normal. 3I Atlas is actively cometary, but showing structures that persist longer and sharper than our models predict. If we extrapolate from 3 examples, the implication is that the population of interstellar objects is heterogeneous. There is no single typical interstellar visitor. They come in different compositions, different sizes, different activity levels, reflecting the diversity of stellar systems they originated from. This diversity is scientifically valuable because it reveals the range of planetary formation conditions across the galaxy. Each interstellar object is a direct sample from another star system. We cannot visit those systems. Even the nearest stars are light years away, unreachable with current technology. But interstellar objects visit us. They bring their chemistry, their structure, their stories encoded in ice and rock. By studying them, we are doing comparative planetology on a galactic scale. We are learning that some stellar systems produce carbon-rich comets. Others produce more rocky bodies. Some eject objects early in their formation, preserving primordial compositions. Others eject objects after billions of years of evolution, carrying the chemical signatures of processed material. The anti-tail mystery of 3I Atlas, regardless of its final explanation, is revealing gaps in our models. Our cometary physics is built on solar system comets, which represent one sample of formation conditions, the specific environment of our solar nebula 4.6 billion years ago. That is one data point in the vast space of possible planetary system chemistries. 3I Atlas is showing us that comets from other systems might not behave the same way. They might have different volatile inventories. They might have different dust properties. They might respond to solar heating and radiation in ways that do not match our predictions, because our predictions were never tested against objects from those environments. That is not a failure of science. That is science working as intended. Models are refined when observations do not match predictions. And the refined models are better, more general, more capable of explaining a wider range of phenomena. Looking forward, the study of interstellar objects is about to explode. The Vera Rubin Observatory, currently under construction in Chile, will begin full operation soon. It is a survey telescope designed to scan the entire visible sky every few nights, detecting transient events and moving objects. Its sensitivity and field of view are optimized to catch faint, fast-moving objects, exactly the profile of interstellar visitors. Current estimates suggest Rubin will detect 1 to 2 interstellar objects per month once it is fully operational. That is not a typo. From 3 confirmed interstellar objects in human history, we are about to jump to dozens per year. Within a decade, we could have a catalog of hundreds, providing statistical samples large enough to characterize the population, identify subtypes, and build robust models of interstellar object properties. That flood of data will contextualize 3I Atlas. Right now, it is one of 3. An unusual behavior makes it an outlier. But if Rubin detects 10 more objects showing similar anti-tail persistence, suddenly 3I Atlas is not an outlier. It is part of a category. If no other object shows this behavior, then 3I Atlas truly is unique. And understanding why becomes even more critical. Either outcome advances knowledge, and the rapid pace of discovery means we will not wait decades for answers. The next few years will transform interstellar object science from a nascent field studying rare curiosities into a mature discipline with datasets, classification schemes, and predictive theories. There is also a philosophical dimension to this research. For most of human history, we could only study what was gravitationally bound to our sun. We mapped the planets. We cataloged asteroids and comets in solar orbit. We inferred the existence of the Oort cloud from long-period comets falling inward. But it was all our stuff, material that belonged to our solar system since its formation. Interstellar objects are someone else's stuff. They are refugees from other stellar systems carrying information about places we cannot reach. Every interstellar object is a message in a bottle thrown into the cosmic ocean by the dynamics of another world. We are reading those messages now, learning the languages of other star systems' formation histories. And if, in the process of reading those messages, we ever encounter an object that defies natural explanation, an object whose structure, trajectory, or composition cannot be reconciled with known astrophysical processes, that would be the most profound message of all. It would mean we are not alone in shaping matter into intentional forms. It would mean intelligence exists elsewhere and has the capability to send objects across interstellar space. That is not the expected outcome for 3I Atlas or any other object we have detected so far. The vast majority of objects will be natural products of stellar and planetary formation with no intentional origin. But the possibility exists, and science requires that we remain open to following evidence wherever it leads. Ruling out artificial origin requires actually checking, not assuming it is impossible because it is unlikely. 3I Atlas is contributing to that foundation. Every measurement, every spectrum, every high-resolution image adds to our library of what interstellar objects look like and how they behave. That library becomes the reference for evaluating future detections. When Rubin finds an object with an unusual acceleration, we will compare it to 3I Atlas and 2I Borisov and Oumuamua. When spectroscopy reveals an exotic molecule, we will check if similar molecules appeared in previous interstellar visitors. Pattern recognition requires patterns, and patterns require data. We are building that dataset now in real time, and everyone following this story is witnessing the early chapters of a field that will define 21st century astronomy. So yes, the anti-tail mystery matters for understanding 3I Atlas specifically, but it also matters for training our observational and theoretical tools on a new class of objects. It matters for refining our models so they are ready for the flood of data coming from Rubin. It matters for establishing what normal looks like in the population of interstellar visitors so we can recognize abnormal when it appears. And it matters because the universe is vast and strange, and every time we look closely at something we assumed we understood, we find surprises. 3I Atlas is this year's surprise. There will be more. And each one teaches us that the cosmos is richer, more complex, and more wonderful than our current understanding captures. That is the essence of exploration. Not knowing what you will find, but being ready to learn when you find it. So what do we actually know? We know that a telescope in Thailand captured images in mid-November showing 3I Atlas with 3 distinct tail structures: an ion tail, a dust tail, and an anti-tail simultaneously visible and sharply defined. We know that the anti-tail, which should have faded to near invisibility by 18 days post-perihelion, is instead maintaining structure and possibly intensifying. We know that multiple independent observations from experienced astronomers around the world confirm this behavior. We know that the standard explanations for anti-tail persistence, large particle populations, fragmentation, directed jets, each have merit, but each also struggles to fully account for the sharpness and duration of the structure we are seeing. And we know that 3I Atlas's interstellar origin means its composition could include exotic ices and materials that behave differently from solar system comets, providing plausible but not yet confirmed mechanisms for its unusual activity. What we do not yet know is the definitive answer. We do not have the spectroscopic velocity measurements that would tell us whether particles are moving at speeds consistent with natural outgassing or something more energetic. We do not have the high-resolution nucleus imaging that would confirm or rule out fragmentation. We do not have the continuous photometric monitoring that would reveal rotation periods and brightness cycles. But here is the crucial point. We are about to get that data. December 19th is 32 days away. Every major telescope that can be tasked is being pointed at this comet. The observation campaign is coordinated, comprehensive, and designed specifically to answer the questions the anti-tail raises. By early January, we will have preliminary results. By late January or February, comprehensive analysis will be published. The mystery has a timer on it, and that timer is counting down. Regardless of the outcome, 3I Atlas has already accomplished something scientifically important. It has challenged our models. It has forced astronomers to reconsider assumptions about post-perihelion behavior in comets, especially interstellar comets with potentially exotic compositions. It has provided a case study that will be referenced in future research on cometary dynamics and interstellar object characterization. And it has demonstrated that the field of interstellar object studies is not just theoretical. It is observational, active, and producing puzzles that require serious investigation. Whether the final explanation is mundane or extraordinary, the process of investigating this comet is advancing our understanding of how comets work, what interstellar visitors are like, and how science approaches anomalies. There is something deeply human about following a mystery like this in real time. We are not reading about a discovery made decades ago and neatly summarized in textbooks. We are watching science happen. We are seeing the observations come in, the discussions unfold, the hypotheses proposed and tested. And we are part of that process, not as passive consumers, but as engaged observers who understand enough to appreciate the stakes. You now know what comets normally do. You know why antitails are temporary. You know the timeline of 3I Atlas's behavior and why each checkpoint where it should have faded becomes another data point in favor of something unusual happening. You understand the competing theories and where each one is strong or weak. You are equipped to follow the December observations and interpret what they mean when the results are announced. That is the value of going deep on a topic like this. Surface-level coverage tells you weird comet has 3 tails and leaves it there. Deep investigation tells you why that is weird, what the implications are, what we are doing to investigate, and what the possible answers might be. It transforms you from a headline consumer into someone who actually understands the science. Someone who can evaluate claims and recognize when evidence supports a conclusion versus when it is still uncertain. That is the kind of scientific literacy that matters in a world overflowing with information, but often lacking in depth. So here is what I need from you. If this kind of cosmic detective work fascinates you, if you are the type of person who wants to understand mysteries at a level deeper than clickbait allows, subscribe to this channel so you do not miss the follow-up, because there will be a follow-up when the December observations come in. When spectroscopy reveals particle velocities, when we have answers instead of questions, I will be covering it here. You will want to see how this resolves. You will want to know whether the exotic ice hypothesis held up, whether the massive particle theory was correct, or whether something entirely unexpected emerged from the data. The story is not over. This video is Chapter 1. December 19th and the subsequent analysis are Chapter 2, and you do not want to miss the conclusion. Drop a comment right now telling me your take. Do you think this is exotic ice composition producing unusual but ultimately natural behavior? Do you think it is massive dust grains maintaining structure through sheer volume? Do you think it is a directed jet from a fortuitously placed vent on the nucleus? Or do you think there is something we have not considered yet? Some mechanism or process that current theories are missing. I am genuinely curious where you land after hearing all the evidence. And if you have been following 3I Atlas since it was first identified, tell me that too. The people who have been tracking this object for months have watched the mystery deepen step by step, and your perspective is valuable. Share this video with anyone in your life who loves space mysteries that actual scientists are actively investigating. Not conspiracy theories, not baseless speculation, but real data producing real questions that require real investigation. This is what science looks like when it is working. It is messy. It is uncertain. Competing explanations coexist until evidence tips the scales. Experts disagree on interpretation. Data is incomplete until more observations fill the gaps. But that process, that rigorous evidence-based approach to understanding the universe, is how we have gone from looking up at the sky in wonder to actually comprehending the mechanics of what we are seeing. And every so often, that process hits something that does not fit the models. And that is when things get truly interesting. 3I Atlas is interesting. Its anti-tale is defying expectations in a way that cannot be dismissed as measurement error or observer bias. Multiple independent confirmations from reputable sources using different equipment establish that this is real. The question now is what mechanism explains it? And 32 days from now, when the comet makes its closest approach and every available telescope captures data designed to answer that question, we will be watching, we will be analyzing, we will be learning. And if you are subscribed, you will be here with me as we break down what the data reveals. December 19th, the comet arrives at optimal observation distance. The telescopes are ready. The spectrographs are calibrated. The observation schedules are set. And in the weeks following, the data will pour in. Velocity measurements, brightness curves, spectral signatures, morphological evolution. That data will either confirm natural explanations or force us to expand the range of possibilities. Either outcome is valuable. Either outcome teaches us something fundamental about comets, about interstellar objects, about how the universe works. And either outcome is something you will want to understand in depth, not just as a headline, but as someone who followed the investigation from mystery through resolution. So stay curious, stay engaged, keep asking questions. Science does not have all the answers yet, but it has a proven method for finding them. And that method is being applied right now to 3I Atlas. We are going to learn something profound from this comet. Whether it is about exotic ice, chemistry, unusual dust dynamics, or something entirely unexpected. And when we do, when the answer finally emerges from the data, it will be satisfying, not because it confirms what we wanted to believe, but because it will be true, verified, tested, supported by evidence gathered through careful observation and rigorous analysis. That is the promise of science. That is why we investigate mysteries instead of just speculating about them. And that is why this story matters beyond just one comet with an unusually persistent anti-tail. It matters because it is a reminder that the universe still holds surprises, that our models are good but not perfect, that there is always more to learn. 3i Atlas is teaching us that lesson right now, and 32 days from now, the next chapter of that lesson begins. I will see you then. And until that moment, keep looking up, keep questioning, and keep digging deeper than the surface allows, because that is where the real understanding lives.